Okay, let's get started. Okay, so today is also hot, and then tomorrow is the game day with Korean University and Semiconductor. Right? Who will attend the game day? Who will? Okay, so let's study hard until today, and then let's enjoy the game day tomorrow. Okay, so in the previous class, I briefly introduced about this course. This course is computer architecture course. So I briefly also explained about the study on computer architecture. Also, I mentioned that recently computers are pervasive. So it means that everyone, every most electric devices can be called computer, okay? The computers, because these devices include processors, and then processors can execute instructions, the defined instructions. So these instructions are defined in instruction set architecture, so called the ISA. So, and then we also learned why we need to learn computer architecture. Okay, so for not to actually indirectly, and then this study is required for building better computer systems. Okay, better computer system means that the higher performance. Just remember that. So we are engineering students. So actually, our research goal and then our study goal is to build better systems. Okay? The better systems means high performance and low cost. But the knowledge on computer architecture is also required for software engineers, right? Because if we know about if we know about the computer system, then we can also build better software or better applications, because these applications run on hardware, so computer systems. So if we can understand about the computer hardware, then we can build the better software and then a better framework. Okay. And then recently, I mentioned that domain-specific applications like the machine learning, so domain-specific software is very popular, right? So then these type of applications demand very high performance hardware system. So which means also, if you can understand the hardware architecture or hardware organizations, then you can also develop the better domain-specific software, right? So that's why we need to study about the computer architecture. Okay, so and then now let's discuss about abstraction. So in the first class, on Tuesday, right? Suppose in the last Tuesday, I explained that the goal of this course is to explore computer system architecture at an abstraction level. Okay, so as a computer science or computer engineering student, then you need to know about the abstraction. Okay, so what is abstraction? What is the meaning of abstraction? So actually, you can think that the abstraction is just simplifying. Okay, the simplifying. Then what? Why? Why do we need to simplify some systems? Why? It is because the target systems can be very, very complex. And then, which means we cannot understand So every detail of this target system, right? So then we can only understand the required knowledge, or we can only understand the some required interface or required signals, and then this this technique or this approach is called abstraction. And then actually in a computer system, the abstraction is very important concept. As I mentioned, the computer systems are very complex. We cannot understand the every detail of computer systems, right? No. Computer hardware is also complex. Also, underneath of this computer hardware, then there is semiconductor technology, and then we cannot understand the technology. But as a but if we just study a certain level or a certain area of computer systems, then we can just focus on this level. But we can simplify the other levels of computer systems. Okay, let's see the example of abstraction in our real world. Actually, in our real world, we frequently use the concept of abstraction, right? So for example, so you can find this photo here. You can find the very cute little girl here, and then she is driving for it. It's not good because I think she is under 18. But okay, so let us assume that you need to drive a car, right? And then you know a car is a very complex system. For example, a very complex system. So actually, a car includes engine and then controllers, and then also a car includes the many different mechanical parts. And then many mechanical parts are controlled by some connections. Okay. So actually, I don't understand about the car system because that's not my major. So you don't. I believe you don't have a deep knowledge about this car system, but we can drive a car without the knowledge of detailed systems of this car, right? So that is the example of abstraction. So this is the abstraction layer. So in order to drive our car, but we need to learn how to drive our car and how to control our car. So for example, in order to drive our car, so we need to learn how to use a handle, right? So we need to know how to use pedals, like the acceleration pedals and then brake pedals, right? But then if we know how to drive our car, then we can drive our car without the knowledge of these car systems. But under this car, we can find the very complex engine and then very complex brake system as other control systems. But we don't need to know about this. So this is the example of car system. So so in order to use our car, we can just understand this interface, right? So under this interface, we can find the very complex component, but we don't need to understand about these complex components. So this is the example of abstraction in our real world. Also another example is the vending machine. So I believe everyone can use the vending machine, but right? So we can just push coin and then we can just push in buttons of the vending machine. But inside of the vending machine, and we can find the control system. Actually, a vending machine includes microcontroller, and then this microcontroller has a very simple program. Then program controller this vending machine. But we don't know how this microcontroller controls this vending machine, but we can use because interface, so like the button and then coin input is revealed to us, and then we can use hardware vending machine using this interface, and that's it. We don't need to understand about the inside of the vending machine. So this is the example of abstraction. Then let's see about the abstraction in computer system. So this is the meaning of the abstraction. So if you took the this logic design course, then you can be very familiar with this figure. So definition is that the hiding details when they are important. So which means that we don't need to understand about the some other details, but we are studying some levels of computer system. Then we need to understand this level. Okay. So as you can see, this is the some layers of computer system. Also, and then as I mentioned, the computer systems are very complex systems. So we can divide the computer system into multiple levels or multiple layers. Okay, so in order to build a single computer system, then actually knowledge on this entire levels is required actually, right? So our computer system includes a processor and memories, and then we already know that processors and memories are semiconductor products, right? So the semiconductor technology is very important and very critical. So which means actually you have to build a computer system, then we require the knowledge on semiconductor technology, and then also below the semiconductor technology, actually we need to learn about the physics, like electric physics or some modern physics. Actually, in order to understand some behavior of semiconductor, then you need to know about some modern physics. But the physics are very difficult study. So actually, I can understand the detailed detailed theory of the physics, like that is on the semiconductor technology. But I can use computers. Also, I working on the computer hardware. So there are some low levels, so like the physics devices and analog circuits. And then for this layer, then there is a digital circuit layer and logic layer. Actually, if you took COSE221, so this is the logic design, then this digital logic design course covers this layer, like the gate level design and logic level design. Okay. And then for this layer, you can find the microarchitecture and architecture, right? And then in this course, we will cover these two layers, like microarchitecture and architecture. So as you can see, for this architecture layer, you can find operating system, and then this operating system is the software, right? So we are focusing on this layer, so which means that we just try to understand the computer systems at an abstraction level of this layer, right? We will not learn about the physical characteristics of the semiconductor. We will not learn about the logic design. So we will not cover about the operating system. Just we will focus on the part of a layer in our computer system. Okay. So just to remember that we just see the computer systems at an abstraction level of architecture and microarchitecture. Okay. And then also, if you see this figure, so this is the hardware part, and then also over the hardware part, then you can find the software part, so operating system. And then architecture is here, right here. So you can say that architecture area is the interface between software and hardware, right? So it's a kind of boundary of software. So under the software, so it is located at the boundary of hardware. So that means you need to understand some knowledge on software and hardware for this course. Okay. Okay, this is the abstraction. And then let's go also example of an abstraction level in the computer system. Actually, the process of design. So what is this? So this is a die-photo of Intel i7 processor. Okay. So it's a very beautiful photo, right? Okay. So then, what can you learn through this photo? So this is the die-photo. So which means that this is the photo of Intel i7 processor. But what can we learn? So what can we understand about the computer system or Intel i7 processor using this photo? Nothing, right? Because so we know that the modern Intel processors include many transistors, right? Actually, a single CPU chip includes billions of transistors. Okay, but if we just see this photo, oh, this is a very beautiful photo, then what? I don't know. We cannot understand about the Intel processor, but on this photo, I added some blocks like these rectangles. And then if you see this photo, then we can know some information about the Intel processor. So if we see this figure, then we can know that, oh, this processor includes 4 cores. So you can find the 4 CPU cores, okay? And then also this processor includes the GPU, integrated GPU. Actually, Intel CPU usually includes the integrated GPU. And then you can also find the L3 cache, okay, around the CPU cores. So it means that these L3 caches are shared by multiple CPU cores, and then its L3 caches are connected via interconnection network. And then system agent or some I/O controllers are here. So we can find the memory controller. So this is the abstraction level of a chip photo or chip surface of chip actually. But using this photo was some very simple block diagram, not block figure, not diagram, then we can understand some information, but slight of information, but we can learn about the Intel processor using. So this is the example of abstraction level. So this abstraction level shows the number of cores, also the location of CPU core. Also it shows the some GPU and then L3 caches and then some paired L3 caches and interconnection network. And that's it. That's what we learned from this figure. Okay. So if you change the abstraction, what? So what I want to say is that what inside of this photo, so there we can find many transistors, but we cannot get any information from these many transistors. Okay, we cannot understand. So details are hidden, like the transistors and how transistors are designed and how transistors are connected. So this information is hidden from this photo, but we can understand some revealed, some it's an abstraction level. So this information is revealed at a certain abstraction level. We can understand some information at this abstraction level. Okay. So let's see the another example. So this is the actually typical architectural view for processor architecture. So architecture is a little bit wide, but so this is the architectural view. So typical architectural view. Okay. So this figure shows how computer architecture instead is the architecture, the researcher on computer architecture and computer system or computer architecture. So, so this figure shows how computer architect understands the structure of processor. So I believe this figure actually the letters are very small. I believe you cannot see these letters, but this photo shows the structure and then structure of inside of Intel core. So as you can see, you can find the core here. So this figure shows the detailed architecture of Intel core. Okay, Intel core. So don't worry about this figure. So actually, so you know this figure looks very complex, but don't worry because in this course we will not cover this complex process architecture. Okay, so we will just cover very simple pipeline process architecture in this course. Okay, but let's see the example of the architectural view, architectural level of this processor. So you can find many blocks, okay? And then each block represents components, okay? But actually, we can design these components using hardware description languages. But so in this figure, we cannot understand how this component is designed. So actually, this block just shows the name of a component, right? Right. So the letters is very small. So you can find this is the decoder, and then this is batch engine. Then also you can find this is the execution unit. Also, we can find these blocks are connected via some arrows, some lines. Okay. So these lines or arrows represent flow of data or flow of control signals, right? So if we see this figure, then we can know, oh, this processor core includes some blocks or some components, and then we can also know many components are connected to each other. And also we can understand how data flows component by. Okay, so this is the example of architectural view. So it's the example of architectural abstraction level. But as I mentioned, inside of this block, actually this block needs to be designed using hardware description language, but these details are hidden. Okay, so for the architecture area, you can understand the structure or architecture or processor at this level, this abstraction level. Okay, so I just explained about the abstraction, the terminology abstraction in computer systems, and then the abstraction level in computer architecture. Then let's see how programs are executed on computer systems. So I believe everyone knows the computers are composed of, or computer is composed of software part and hardware part. But actually, users communicate with software, right? Application software. So this is the real world. It's a world, the real world. And then actually this is the interface between a computer system and real world. So we can find that we can just see how this application software works on computer systems. Okay. But under this application software, we can find the system software and hardware, right? So which means that in order to run our application software, then we require system software and hardware, right? So this is what we see on computer systems, the application software. So usually this is the real software such as the office programs or internet browser, also some other applications. Okay, and then this software is written in high-level language, programming language such as C, C++, Java, Go, Swift, and Python. And then, so this is just the software that we can write a code using this software. Also, ChatGPT can write a code using this high-level programming language, right? The machine can also program. Machine can also write a code. But under this application software, we can find the system software, and then there are two types of system software. The one is compiler, and then the other is the operating system. So actually, we can write a code using high-level language, and then this programming language is very similar to our natural language, right? So if you see the syntax of C or C++, then we can easily understand if we can understand English, right? But computers cannot understand our natural language because a computer or computer hardware is the system. And then digital systems can only understand digital signals, and then digital signal is composed of 0 and 1. Okay. So which means that a program code needs to be translated. And in order to translate this program code, then we require compiler. So this is the role of the compiler. The role of a compiler is to translate high-level language code into machine code. So this compiler is also called a system software. And then operating system. Our application run on operating system. So actually, we can say that operating system is also a true interface of an interface between application software and hardware. Okay. So operating system manages the hardware, also control the hardware. Also operating system manage the threads or processes, okay, on the computer system. Okay. So you will learn about the operating system the next semester, right? Okay, so the operating system is also required. And then under the operating system, we can find hardware. The hardware includes the hardware components such as processors and memories and I/O devices. Okay. And then let's see how program code is translated. Okay. So as I mentioned, so we can write a code using high-level language. Okay. But so this is also the concept of abstraction. So actually, we can just understand the syntax of this high-level languages, also how the code is executed by this high-level language. So we don't need to understand about the actually abstraction, so this assembly code. But in this course, you need to understand how you need to understand the meaning of assembly instructions, right? But if we just write a code using a high-level language, high-level programming language, then you don't need to understand about the assembly language. Okay? So this is the example code in C. And then by compiler, this example code is translated into assembly language code. Okay. So on Linux, then we can use compiler called the GCC, right? GCC means the GNU-C compiler. So this GCC can compile the code into the assembly code. So actually, GCC directly generates the binary code like this. But if you use -S option, then the assembly code is generated. Okay? So firstly, compiler translates this high-level language code into assembly code. Okay? If you see that this assembly code, you can find the several assembly instructions. So you can find some unknown characters, okay, like x1, x2, x3. So we will learn about this unknown characters in chapter 2. Okay? Then, but this is, but this is, you can find this is the characters of English. So actually, the computer hardware cannot understand the English characters. So this assembly code also needs to be translated. So it should be translated into the machine language or machine code. Then we can use the assembler. But usually, as I mentioned, our compilers directly generate this machine code from high-level language. Okay. So if you see that this machine code, you can find that there are many zeros and ones here because, as I mentioned, a processor can understand only digital signal, and then digital signal is composed of 0 and 1. So actually, this one line is mapped to this one line of machine code. So the assembler just translates this assembly instruction into machine code. Okay. Then computer can read this code, and then computer's processor actually a processor can read this code, and processor can run code. Okay. That's how the program is translated and executed by computer hardware. Okay. Then let's see how computer system is organized. So as I mentioned, this is the hardware related course. So and then also you need to learn how the software is interacting with hardware. It's hardware. So which means that we need to also know how computer hardware is organized. Okay. So let's see the components of a typical the computer system. So what is this? What is this? Huh? So, so actually, so recently we use laptop computers, which means that we cannot see the inside of our laptop computers. Okay, but if we use a desktop computer, then you can open the chassis of the desktop computers and you can find the main board, right? So actually, also our laptop computer also has a main board, but we cannot open the lid of our laptop computers because our computers are very expensive. But actually, inside our computer, we can find a main board. This main board is called a motherboard. Okay. So actually, this is the photo of own main board. Okay. So actually, so the structure of main the main board is slightly different from the this structure of this main board. Okay, because this is the some main board for old generation CPUs. But we can also from this figure or from this photo, we can understand many components. Many hardware components are actually required for building computer system, right? So this is the CPU socket. Okay, we can put CPU, which means processor, to this socket, and also you can find the memory slot, the DIMM slot here, and also you can find the main board chip here. Okay, like here. So which means in a computer system, we also connect multiple components or multiple hardware components. Then you can build a single computer system. So then let's see how the computer systems are organized. So this is the typical organization of a computer system, but this is the you can find the old here. So which means that this is the typical organization of computer system, but this is the old generation, for the old generation CPUs. So what can you see? The CPU is here. So this is the processor. So which means that a machine instruction. The machine instructions are given to CPU, and then CPU generates define output. Okay, so I will explain about this concept in chapter 2 also. But you need to remember that in the CPU execute instruction, and then execute means that generate the define output. Okay, so this is the main component of a computer system. So you can find that the memory. Our memory is connected to the CPU via memory bus. What is bus? It's a bus. It's not a vehicle. It's not a vehicle, right? What is bus? It's communication channels. Okay. Actually, if you see the detailed view of the CPU and memory, then you can find that many wires are connected between CPU and memory. Okay, and then using these wires, then electric signals are go and communicate between CPUs and memory. So and then these communication channels are called bus. Okay, so using the memory bus, then CPU receives data from memory. Also, the data can be stored in memory. Okay. Also, you can find that this bus is T, right? Which means that it requires high bandwidth. Okay. So bandwidth means the amount of data per unit time. Okay. So which means that this channel requires high bandwidth. And then also you can find the general I/O bus here. Bus is also the communication channel. And then GPU is also connected to this bus. And then you can find the several I/O devices here. And what can we know? What can we know from this figure? Actually, these devices, memory, GPU, and I/O devices are connected to CPU because the CPU is the main processor. Okay, so it's a central processor. So actually, every instruction is executed by CPU, and then the CPU is connected to other hardware components. Okay, how can you know from this figure? So you can find that, oh, CPU is connected to many devices. But also I explained that the thickness of this line represent bandwidth. So IO devices are connected to CPU hierarchically. So which means that, so actually CPU frequently communicate with memory. And then I mentioned that for this communication between CPU and memory, we require very high bandwidth communication channel. So that's why the memory is located near CPU. Also, memory and CPU is connected via high bandwidth channel or high bandwidth bus. So this bus is big. And then you can also find the GPU in here, and then how about the IO devices? IO devices, actually keyboards, mice, storage, and then network card. These are examples of IO devices. What is the common characteristics of this IO devices? Keyboard, mice, network. It's slow, right? Even though we type very fast, but the keyboards are very slow device compared to CPU. CPU works with a very high frequency, right? But even though we type our keyboard very quickly, but it's very, very, very slow. So again, this is the IO device, but this is very slow. And then this device far from CPU, also the bandwidth is low. Okay. So, and also another feature is that because these IO devices are very slow, actually IO devices are controlled by operating systems. It's software because it's very, very slow. But memory is fast. Memory should be fast for better control system. So that's why the memory is located near CPU, and then memory is main memory. The main memory is controlled by hardware. Okay. So using this figure, you can know some information regarding computer systems. So, and then, well, you can find that there are two chips here, two motherboard chips here. And then I said that this is the photo of old generation motherboard. And then recently, actually, this chip is called a North Bridge chip. So North Bridge chip, and then this chip is called a South Bridge chip. And recently, North Bridge chip is included in the CPU. Okay, so this is the architecture of the modern computer system. So North Bridge part is included, and then the CPU is directly communicated with memory and GPU. And then I mentioned that if so this bus is very big, which means that this communication channel requires very high bandwidth. Also recently, GPUs also require very high data bandwidth. Okay, and so that's why the CPU includes North Bridge part, North Bridge chip, and then directly communicate with memory and GPUs. Also, you can find the IO chip here. This is the South Bridge part. And then this South Bridge chip handles the very slow IO device. This is the modern organization of a modern computer system. Okay. And then also you can find this figure from the Intel motherboard, this Intel mainboard chip specification. Okay. So you can, if you see this figure, then you can understand how a computer system how a computer system is built. Okay, as I mentioned, this is the CPU, and then CPU is connected to the motherboard chip. So it's the mainboard chip, and the mainboard chip handles the communication between low I/O devices. And then CPU directly communicates with the GPUs and main memory. Okay, that is the simple diagram of a computer system. So this is the simple organization of a typical computer system. Okay. Okay. So until now, I briefly explained how to build a computer system. So it's a computer hardware. So this is the common sense and a common knowledge you need to know as a computer engineering student. Okay. Okay. Then let's learn the technology. Technology in the processor, computer processors and memory. So what does it mean? What is the technology? So it means the semiconductor technology. Okay. Okay. Then question. What is semiconductor? So everyone knows that using semiconductor technology, we can make processors and memory, like DRAM or flash memory, something like that. Then, what is semiconductor? Why is semiconductor so important or critical? Common sense, actually. What is semiconductor? Who knows? Okay. Okay, semi means it's kind of half. And then what is the conductor? The conductor means that electrons can flow via conductor materials, right? It's like the copper wire or metal wire. So it means that electric currents. So it means electric currents can flow via is conductor materials. So it means in Korean it's called 도체, 맞죠? 도체. So it means that electric currents can flow. Then semiconductor means it's half conductor. What does that mean? It means this semiconductor material can work like conductor or insulator. So insulator is the opposite concept of the conductor, which means that electric current cannot flow via insulator. So semiconductor means that a same material can work like conductor or can work like insulator. Okay, that is the meaning of semiconductor. Why? Why is it critical? We can control. So, which means that we can change the characteristics. Like if we just change a certain condition, then a same material can work as conductor. But if we change this condition, then the same material can work like insulator. Okay, it's controlled. Actually, this characteristics can be controlled by voltage level. So electric, so actually the amount of charge, the voltage level. So that is the meaning of semiconductor. So it means that we can control electric currents, well, we can control the flow of electric currents using other electric signals. And so which means it's a controllable. That's very important to build stable systems, right? It's very important. If we can control something stably, then we can build stable systems. So based on this theory, this concept, then we can build very complex logics. We can build very complex business systems. Then we can build very complex processors, right? That's why semiconductor technology is very critical for our electric devices or digital systems. So let's see then. I mentioned that actually the processor, like if the CPUs or if CPUs are product of semiconductor technology, then it means that semiconductor technology is also very important. It's very critical for the performance and then cost of these processors. I believe someone have heard about the 7-nanometer technology. Oops, my writing is not good. Like the 7-nanometer technology or 5-nanometer, then 3-nanometer technology by TSMC or Samsung. So what does that mean? This number, 7-nanometer, 5-nanometer, 3-nanometer. So actually, this number represents the level of semiconductor technology. So which means, which one is better? 7-nanometer, 5-nanometer, 3-nanometer? 3, right? Because actually this number represents the width of CMOS transistor channel. Okay. So this means actually, so you can understand that this number represents the size of a single transistor. Okay, it's relative to the size, not actually the size of the transistor, but you can understand that if this number is small, so which means we can make smaller transistors. Okay, so what does that mean? I mentioned Intel CPU includes billions of transistors, right? It's billions, so many. And then if we can make smaller transistors, which means we can include more transistors in the same area. Why is it important? The transistor is required for building the systems or digital components. So we can use more transistors. We can use more complex. So which means better. Okay, we can build better processors. We can build more complex processors. So which means the area is the same, but if the transistor size is small, so we can build better transistors, better processors. So actually, this transistor size is decreased. Transistor size has decreased year by year. Okay. So later I will explain about the Moore's law. It's a very important law that contracts the computer industry. But so you need to remember that this number is very critical and this number is very important for is using this number, the 3 nanometer, 5 nanometer, 7 nanometer, then we can understand how the semiconductor technology has been developed. And then if this number is small, which means, oh, transistor size is small. And then smallest transistor is better. Okay? Using better transistors, we can build better processors. So this table shows the you can find the year here, and then actually you can build the processors using transistors, and then also in the early area of the actually 1951, and you can be the processors was built using vacuum tube. So you can find that in this table, you can find the relative performance per cost. So what can you know? So it's very, very old. It's 1951. Then it's 2013. So you can find that relative performance per cost is has increased dramatically. Okay. So if this is 1, then nowadays the performance per transistor is very, very high. How? We can use smaller transistor. Then the cost is reduced, performance is increased. Okay? That's why the semiconductor technology is critical for the performance and cost of processors. As I mentioned, transistor is smaller and performance is higher, cost is lower. Which means if a transistor size is smaller, then we can build higher performance CPU than lower cost CPU. Okay, that's why the semiconductor technology is very critical. Then let's see how to manufacture CPU using silicon. Okay, and then the silicon is the main material for semiconductor, right? SI is the silicon, right? SI. Then this is the main element for SEM, right? So actually, using this silicon, we can build semiconductor. So this is the silicon ingot. So which is the kind of pure silicon, and then this ingot means that it's a cylinder. It's a cylinder. And then actually we can cut the cylinder horizontally, and we can make the blank wafers. Okay, this is the photo of wafer. This is a circular form, and then as I mentioned that the silicon ingot is the cylinder, the pure silicon, and then if we just cut this cylinder the horizontally, then we can get this wafer. And then on the wafer, and then using the ultraviolet ray or some other light, and we can make the wire and semiconductor. So which means that we can make a chip. And then this a single chip is called actually die. Okay. So on the surface of the silicon wafer, then we can make chip, but these chips can include defects like the errors. And then if some other materials are included during the manufacturing, then defects will be included in the chip, and we cannot use these chips. Okay, so we need to test the manufactured chips. So then if the defects are found, then these chips are thrown away. Okay, we cannot use these chips, defective chips. Okay, then the chip is packaged and then the tested, and then this packaged chip is delivered to the computer manufacturers. So this is the typical process of semi, uh, semiconductor manufacturing. So which means that it's the typical process for CPU manufacturing. And then usually this manufacturing is done by TSMC, the Taiwan semiconductor company. Also in Korea, it is performed by Samsung. And then in America, it's performed by Intel. Okay, but usually the TSMC and Samsung have better technology for manufacturing IC. Okay. Then let's see the photo of this I7 wafer. So in this photo, so you can find that this is the circular wafer. Actually, circle shape. The wafer is circle shaped, and then you can find the small rectangles here. So this is a single chip, and then this single chip is called die. So actually, you can find that for this chip is cut. So part of this chip is under this boundary of the circle. So actually, you cannot use this chip actually. The shape of a chip or shape of a die is rectangle. Okay? So what can be found? So the diameter of this wafer is 300 millimeter. And then you can find 280 chip. What is the technology? Semiconductor technology is 32 nanometer. Okay. And then this is the chip size. Okay. So you can find another wafer here. So it's also the i7 processor, wafer of the i7 processor for Intel 10th generation. It's a more recent Intel CPU. The size of wafer is the same, right? The diameter is 300 millimeter. But how many chips? 500 chips. What is different? The wafer size is the same, right? But there are more chips. What is different? Right. You can find, in the previous page, the semiconductor technology is 32 nanometer. Then it's 10 nanometer technology. Also, you can find the chip size here. This is the size of the single chip, and then on this wafer, the size of the single chip is 20 by 10 millimeter. It's around the 200 square millimeter, right? But how about this? It's around the 110 square millimeter, right? It's smaller. You know, the 10th generation may include more transistors, but the size is smaller. And because the size is smaller, and we can get more chips or more dies from the same wafer. This is good. We can reduce the cost, but performance is better. That's why the semiconductor technology is critical. It's a 10 nanometer versus 32 nanometer. Okay? The size is reduced, and we can get more chips. Also, another important factor is yield. So you don't need to know about the yield in this course, but it's just a common sense, common knowledge. Okay, so yield means that is it the top from these chips. So we need to test the chip, and then we cannot use defective chips. Okay, So yield means that is the percentage of to chip from entire chips. Okay, that is the yield. So actually the yield is influenced by effect per area. So which means that so effect per area can be similar for the same semiconductor technology. Okay, so the defect rate. So which means the defect per area. So which means if the chip size is large, then this chip may include effect with higher probability, right? Because the area is large, and then actually the defect per area is similar by semiconductor technology. So which means if the area is large, then this chip may include effects with higher probability. So that's why the larger chip is very, very expensive. And then that's why we need to, everyone likes small chips. Okay. But so that's why the Intel processor is how much much more expensive than Intel personal i7 processor because the area is much larger because Intel Xeon includes more cores. Okay, so yield is also influenced by defect per area. So this is the common sense and the semiconductor technology. So, but just remember that this size of transistor is very, very critical. Okay. Okay, so I just explained about the some technology of the processor. Yeah, any questions? Question? No? Okay. So now we have 7 minutes, and then so I will just discuss about the performance of system. So that I just use the analogy, okay, the performance. So actually, this performance is the main topic of chapter 1, right? Chapter 1. In the syllabus, you can find that performance metric is what we need to learn in this course. So the performance, and then let's see how we can measure the performance of a computer system. But in this time, I'll just use the analogy of performance in the real world. Okay. So as I mentioned, so we frequently compare the performance of two different systems, right? So if you buy new smartphone, then you can just compare the performance of this new smartphone with the old smartphone, right? Why do we purchase new smartphone? It is because new smartphone is better, which means it's faster, right? And then this new smartphone can run games with the best speed, right? So actually, in a real world, we frequently compare performance of different systems, right? So for example, airplane, we can just compare the performance of airplane. How? But we can define different performance metrics for airplanes. So let's the example. So this is the analogy. So just the example. So in this graph, we just compare the passenger capacity of different airplanes. Okay, we can say that this is performance. Why? If a single airplane can carry more people, more people, and we can say that, oh, this airplane is better than that airplane because this airplane can carry more people, right? Which is the best? Air Force A380. Okay? Because number of people, the passenger capacity is the highest. But we can use the different metric, like the cruising range. Cruising range means the distance by the flight distance by airplane, right? Which one is better? Boeing 777, right? How about the cruising speed? So we can compare the speed of the airplane, and then we can find, oh, what is this one? Concorde. This is the old airplane actually. And then Concorde is the best. So what can you know from this example? We frequently use actually terminology performance for comparing different systems, but we can find different concepts of performance, or different definition of performance. So if we just compare the number of passengers, right? It's also important. So if we just buy an airplane and we want a single airplane can carry many people, right? Capacity is also important. Also, speed can be also important, right? Then how can we measure? How can we measure the performance of an airplane? So we need to define how to measure the different systems. It's also same for the computer systems. We can easily say that, oh, this computer is better than that computer, and that is why? Oh, it's faster. But it means for comparing the performance of two different computer systems, we just define performance is just speed. Then actually that is the execution time. Okay. So in that case, we use execution time as a performance metric for comparing two different computers. But we can use the other metric. For example, oh, this is the computer A, and then this is the computer B. During the same time, A can run 10 applications, and then B can run 5 applications. Which is better? We can say that, oh, A is better, but we just compare amount of workload for this case, not speed. The time is the same, but we just compare the amount of jobs or amount of work done by two different computers. So we can use this definition as a performance of computers. Okay? So also same for the other system like the airplane. So actually I just explained about the response time and throughput. Okay, and then we frequently use these two performance metrics for comparing the performance of a computer system. So what is the response time? Just I will end the class. So response time is just the time for executing the same application or same task. So which is faster? What is the throughput? As I mentioned, this is the amount of work done within the same time. Okay, that is the throughput. So the next class we will just I just explained the details of the performance metric of computer. Okay. Any questions? Okay, thank you for listening. Then, enjoy some game one. 감사합니다.